So let's recap what we have done last time. Just the two most important slides. We say that we were looking at a new system. This system is a spin system, and it is placed under an external magnetic field in our real 3D space. The magnetic field is pointing down. The reason it's pointing down just because we chose to have it pointing down. It can be any direction, right? So it is pointing down. We define just our definition. Up is positive z hat, right? So pointing down needs to be negative b0 z hat because b0 here we assume it is a positive number. So under this situation, last time we have gone through the math, right? Particularly for this line, right? We say that if it is an electron, if it is spinning down, it's spin down, it means its angular momentum is pointing down. Okay, just take it for granted. We say spin is not really a spin, not really something spinning, but it's just like classically, just think of that. Okay, an object spinning or moving in circular motion, you have angular momentum pointing down. But because this is an electron with negative charge, so its magnetic moment is pointing up. Okay, that's it, right? If you want to understand the detail, that is fine. If not, this is the minimum you need to know. Positive charge and negative charge have different relationship for the spin or the so-called or the related angular momentum against the magnetic moment. And we also know about the interaction Hamiltonian of the between the spin, right, and the magnetic moment, between the magnetic moment and the magnetic field is negative mu dot b, right? So as a result, if you have magnetic moment pointing up, or in the, so look at this. Now for this figure, I have the magnetic field pointing up, not pointing down. Okay, you have the magnetic moment pointing up, or they are in the same direction. They are parallel, right? When mu is parallel to b, pointing in the same direction, you have a lower energy. This is called Zeeman splitting. And then if you have an opposite direction, you have a higher energy. Is this okay? And let's go back to this figure. We are actually talking about pointing down. So if your spin is in the opposite direction, means the magnetic moment is parallel. Again, for electron, magnetic moment is opposite to the angular momentum. Okay? So that's why this is a lower state. So this will be something you want to have in your mind in the following class, right? And then use this one to, sometimes you do need to have a reference, coordinates for you to think. So what we were doing was the construction of the Hamiltonian under this, not this setup, sorry, this is just to relate the magnetic moment to the magnetic field, right? Our setup is magnetic field pointing down, not pointing up, okay? So we're talking about this experimental setup with the magnetic field pointing down. Then we've gone through the math. We say that, okay, this measurement corresponds to a certain operator. We're measuring the energy. We have been emphasizing this many times. What is a quantum mechanical measurement? You collapse the wave function. But each measurement corresponds to an operator. And here the operator is the Hamiltonian because we are measuring the energy. And this Hamiltonian has two eigenvalues. And we have already said that whenever you do the measurement, the output is the eigenvalue of the corresponding operator. So the output must be the eigenvalue of the Hamiltonian. So we say that, okay, I just call spin up as 0, spin down as 1, just like here. Spin up is 0, spin down is 1. And I know spin up has a lower energy and spin down has a higher energy, right? So due to this equation, H equal to negative mu dot B, then I know that spin down has negative mu times B in magnitude, And then spin up has the measurement or the eigenenergy of this one. And then we just go through this math. I won't go through again. Basically, this Hamiltonian is negative mu times speed and magnitude times sigma c. Any questions? Now, maybe it's worth to waste a little bit more time to revisit this figure. I have been emphasizing many times, the broad sphere is where the state resides, but it is not really in our real 3D space. We say that last time we proved that we can reduce the state to 2 degrees of freedom, right? Phi and theta. And we embed it in the real 3D space. But this embedding is not just for this. You start seeing some relationship to our real 3D space. For example, in our real 3D space, I have the magnetic field pointing down. And turn out its eigenstates are these 2 poles along this z direction. Indeed, if you have the magnetic field pointing in the x direction, then its eigenvalues are going to be plus and minus. So this is, you can say accidental or whatever, but this gives you a feeling of why this is called spin up and this is called spin down. Because it does correlate to the direction of the magnetic field in the real 3D space, right? Without this magnetic field, we don't have degeneracy. They have the same energy. Now, because of the magnetic field are these 2 eigenstates, at the same time, they have different eigenenergy. Okay, I don't know if you fully understand, but we will just keep repeating, keep thinking about this. Then you will appreciate more why this broad sphere has so much special meaning in the 3D space. Although the states do not reside in the 3D space. Again, 0 plus 1 is not equal to nothing. This is not a vector in the 3D space. Okay, questions? For those online, if you have questions, please let me know. Let me just check email, make sure that other students can join because I don't see many students here. Just in case they email. Okay, I don't see any emails. Good. Okay, then today what we want to do is to look at the first thing, the Larmor precession. We have the Hamiltonian already. Then what happened when we put the qubit in this has external magnetic field? So here I show the experimental setup again. In the real 3D space, I have the magnetic field pointing down, right? And then what I'm going to tell you is that the state will rotate about the z-axis when you have this magnetic field. And this is called Larmor precession. And it's related to the qubit frequency. And let's see why, okay? First of all, let's look at the state. A general state has a general state is equal to alpha 0 plus beta 1. This is always correct, right? And this is under a magnetic field, B equals to negative B0 Z hat. That is what we already said. And now we bring in the Schrödinger equation. It's okay, you forgot what it is, right? But you should know that it is this when I write it to you. The rate of change of the state is equal to the Hamiltonian times the state itself. Okay? Of course, what is the state now? The state is alpha beta, right? I write it in the column form. Okay? This we had this before already. Partial t equals to, and what is the Hamiltonian? We actually know that already. The Hamiltonian is just equals to mu b and b0. Or instead of b0, I mean, I want to put a vector for now, right? It's just the magnitude of these 2 vectors times what? Sigma c. Right, yeah, very good. Sigma c, right? So here, let me just detract a little bit. What is mu b? again, mu B is the magnetic moment, right, of what? Electron. And we say this is equals to, what? Actually, why do I call it mu B? I should just call it mu, sorry. Right, this is just the mu, right? The magnetic moment. But this is the electron, so its magnitude equals to what? What do we call the magnetic moment of an electron? Do you remember the name? The Bohr magneton. Okay, just the magnetic moment of an electron, approximately, right? And what is the magnitude of B? Based on this equation, negative B0 Z hat, what is the magnitude? This one. What's the size of, what's the length of Z hat? Well, oh, okay, very good. For Z hat is 1, right? But then the whole thing is B0. Thank you. Right? So that's why I can further write this equation as two equations, like what I said last time. So as a result, I have I H bar partial. Actually, let me, I skip again. Let me just write it down so that get into problem. I want to further spell it out. Then I H bar partial alpha partial T partial beta partial T, the whole thing equals to, and here I forgot the state, sorry, right? I forgot the state. I should also put in the state. I only have the Hamiltonian. On here, it should be alpha beta. Is this okay? I missed this term just now because this is H times psi. Okay? So, and then this is just equal to mu B, as you said, B0, and then times Z, 1 sigma Z, 1, 0, 0, negative 1 times alpha beta. Make sense? And this gives me two equations. Which two equations? The first equation is I H bar partial alpha partial T equals to negative mu B B0 alpha. The second equation is I H bar partial beta partial T equals to mu B B B0 beta. This is the second equation. Do you see how I get this one? Anyone help me to explain how I get this one? How I get the second equation? Anyone doesn't understand? So everyone understand, right? Someone tell me, how do I get this equation again?
You just multiply the matrix with the vector, and then you're only left with the B term, and then you set that equal to the B term on the left side.
Excellent. So he said that we need to equate, this is a vector, left equal to right, right? So the second elements must be equal to the second element on the right. So he said that you do the multiplication of matrix. So you have 0 times alpha minus beta, it is the second element. So that's why I H bar partial B partial T equals to negative B0 B0, I mean mu B B0 times negative beta, and that's why you get this one. Okay, this is need to be very clear. If you know how to do it, then the rest is very simple, right? Now, of course, I don't expect you to remember how you solve differential equation, but this is a simple one. That doesn't matter. You can ask ChatGPT, but you need to understand what's going on. And basically, what is the solution? If you remember, it's an exponential solution, right? So alpha as a function of t is going to be equal to alpha at t equal to 0, right, times e to the power negative mu b B0 divided by I H bar times T. Maybe I should just do this. I don't write it well. Okay? And then the other one is what? Beta of T equals to beta at T equal to 0, e to power mu B B0 divided by I H bar times T. I'm not going to prove it. If you're familiar with this, you get it already. Otherwise, what you can do, just substitute this to here. Substitute alpha of T to here. Do a differentiation. E to the power something times T after differentiation give you that thing times e to the power the whole thing. And then you will find that this is correct. But the important thing is that I'm showing you that this is exponential, but remember I have an I here, so it's not decreasing, it's oscillating because it's e to the power I something, right? Because e to the power I something is cosine something plus I sine something. So it's oscillating, okay? So here I will want to ask, what is alpha t equal to 0? Alpha t equal to 0, I can call it alpha 0. What does it mean? It means at time equal to 0, the value of alpha at time equal to 0, right? So I can call it anything, but if you remember, it is equals to cosine theta 0 over 2, since I say that it is the initial angle, times e to the power negative I phi 0 over 2. Remember, this is another form for the state, right? Instead of alpha 0 plus beta 1, the another form is what? Cosine theta 0 divided by 2, e to the power negative phi divided by 2. Is that okay? So that is alpha 0, right? How about beta 0? I mean beta t equals 0. It's the same, it's just beta 0, but then this is the coefficient for 1, for the basis state 1. So what is that? Do you remember? It's kind of opposite, right? Not opposite, but you know, of alpha. What is that? What is the opposite? Not opposite of sine, but sine theta over 2. Thank you. And then e to the I phi 0 over 2. Yeah, very good. That's how I memorize. The first is cosine. Second cannot be cosine because you can factorize. So it's sine. And then I remember the first is negative. Then the next one is positive. And it has to be phi over 2, right? So this is what we have. Is this okay? Now basically I'm done, right? So now I can say what is the state as a function of time. I just repeat it one more time. Alpha t, the state as a function of time, of course, is the change of alpha and beta as a function of time. And I just show you that it is equal to alpha 0 right? But I'm going to do a transformation, operation is equal to e to the power I mu b B0 divided by h bar t. Okay, 0 plus beta 0 e to the power negative I mu b B0 divided by h bar t, 1. I did not do anything new, one thing new only. But basically, I just copied this one. Alpha equal this whole thing, right? I copied this to here. But it was negative here. Now it becomes positive. Why? Can you see carefully? This is negative divided by I. That's why I put it up, it becomes positive I. Okay? Same for this one, it was positive 1 over I. So it is equal to negative 1 over I. Okay, so I did not do anything new. I just copied this one, right? But now I'm going to plug in alpha 0 also, because alpha 0 was the initial value. So I have cosine theta 0 over 2 e to the power negative I phi 0 over 2, and then e to the power I mu b 0 over h bar t. The whole thing is in front of 0. Then the second one, it is sine theta 0 over 2 e to the power I phi 0 over 2, and then e to the power negative I mu b 0 over h bar t, the whole thing in front of 1. Again, nothing new, right? I just tell you that, okay, you have an initial state, of course, when t equals 0. This term is 1, this term is 1. And I solve that. This term is going to evolve as e to the power I mu b over h bar t. I showed that already when we solved the Schrodinger equation. Then, but if you look at this carefully, you find that this term are very similar, these two terms. I actually can combine it, it becomes cosine theta 0 over 2 e to the power negative I phi over 2. I don't have the phi not here, okay? Plus sine theta 0 over 2 e to the power I phi over 2, 1. Where phi is just equals to phi 0 minus 2 mu b divided by h bar t. If I multiply these two together, then it's just the addition of the exponents. I take out negative I over 2. Then the first one is phi 0. This one take out negative I over 2. Then, of course, it becomes negative. I don't have 2, so I need to multiply by 2, right? Is that okay? If you go to here, it is the same. By using the same definition, I take out I over 2, then I left with phi over 2. I take out I over 2, then this needs to be negative 2b mu b 0 h bar t. But look at this. What is the meaning of this? This is again a state, right? And it is in the form that I can understand. It means it has a polar angle of theta 0. And it also has a azimuthal angle of phi. However, this phi is a variable dependent on t. So basically what it's trying to say, okay, you have this initial state, phi. Then after you put in this magnetic field, your phi 0 doesn't change. So what you're trying to say is, this phi is always equals to phi 0. But this phi is equal to phi 0 minus 2 mu b over h bar t. Is that okay? Then what is the meaning of this based on that? You see, the state is that you always keep theta 0, but your phi is changing. So if it is changing, it means you are doing circular motion on this sphere, right? On this circle. So it's precessing, it's moving as a function of t. And this is called Larmor precession. So maybe a lot of math, but you need to go back to think again if this is not clear. But basically what we have done is, we say you start with alpha beta. I solve the Schrodinger equation. I have the Hamiltonian due to this external magnetic field. Then I realize that the alpha is going to change following this equation. Beta is going to change following this equation. Yeah, of course I know it is going to change. Of course, then you can plot it using computer. But however, if I try to express everything in the polar coordinates, I realize that yes, alpha is changing, but it turned out that alpha and beta are changing, but they change in a way that theta 0 doesn't change. and phi is changing in a constant rate because this is linear in t. So I say that, okay, great, now I understand when it is under an external magnetic field, it will precess. This is called Larmor precession about the z-axis. Any questions? Now, this is the phi. It's just like distance equal to initial distance minus the velocity times time, right? So this is the same. There is an angle, so we can define something called Larmor frequency equals to d phi dt, right? But we take the absolute value, that is equal to 2 mu b b0 divided by h bar. And if you try to plug in 2 mu b, which is the Bohr magneton, EH bar divided by 2m, right? Then you will get this one to be equal to E B0 divided by m, or it is equals to the gamma of B0. Again, this gamma is what? This gamma is the gyromagnetic ratio. Okay? Maybe you forgot already. But the gyromagnetic ratio is the ratio between the magnetic moment and angular momentum that we studied last time, right? But if now you forgot, I don't force you to memorize. It's better you understand, right? Otherwise, in your interview, who's going to hire you if you don't know that? You say you learn this, but you don't understand this, right? Spend some time to memorize. But the point is that now you see that it is oscillating with this angular frequency. Remember, this is angular frequency, so 2 pi times f. Okay? So, of course, then, let me ask you something. If delta phi equals to pi, so I try to turn on the magnetic for a certain time, then you will precess for pi, right? Then what do you get? Then it means that EB0 over m, which is the EB0 over m is the angular frequency, right? The angular frequency times time equal to pi. It means that I want it to rotate by pi, 360 degrees. This gives us t equal to m pi over E beta 0. If I can turn on the external magnetic field for this amount of time, I actually have implemented the Z gate. Because I did not review this time, but in the last lecture, remember, I showed you how to implement a phase shift gate. We say that it's just a rotation about the z-axis, but by that angle, right? So if I can turn on the magnetic field by this amount, I have implemented Z gate or sigma Z. Now, of course, in real quantum computing, I need to remark, usually we don't need Z gate. It's important to understand Larmor frequency because you need to learn about detuning later, right? And also this is very fundamental, right? But usually, they have so-called the virtual Z gate. Basically, you don't really do any Z gate, you just do change of frame, reference frame, to achieve the Z gate. So instead of you really rotating it, you just rotate yourself. Then you will see that it's going in that direction. So we don't need to go to this detail. So basically, just I want you to know that usually you don't do that. Why? Because a large magnetic field is very difficult to turn on and turn off. You need to be fast. Okay, but however, this one set up a very important thing. Remember, we have two levels because of this external magnetic field. If you don't have external magnetic field, you don't have the two level, you cannot form a 2-qubit system, 1-qubit system. You don't have the Hilbert space. Then you cannot do anything. So we turn this on, we do get this Larmor precession, we just let it precessing, but we are going to work on the rotating frame of this Larmor frequency. But at this moment, let's don't worry about that, but we treat it as a gate, right? Just imagine. The main point is now, you have a very simple math and you realize how to make a quantum gate. You already make a quantum gate, also this is not practical. Any questions? Yeah. GE by 2m. How come you know that? Thank you. G by 2m. Yes. Because G is about 2, right? You're good. You're okay.
Can you use on just any particle?
Huh?
Or can you like apply an external magnetic field on just any particle to have this Larmor precession? Or specifically, it has to be like a qubit. What does a qubit look like?
So no, so this has nothing to do with qubit, right? Qubit is just that you use them for quantum computer, you call it qubit. The main point here is they have spin and they have this magnetic moment. So you have magnetic moment, then you will have this precession. And now we use it as a qubit, so we particularly emphasize the states of this broad sphere. Because you have spin, then whether you call it qubit or not, you do have this broad sphere if it is just two state, right? A two-dimensional system.
Do all particles have spin?
Not all particles have spin, yeah.
Oh, okay.
And not all particles have half spin, some are integral spin. So yeah, so not all of them. Okay. So for example, you put the light, I think light spin 0 or 1. Spin 1. Yeah, it's integral spin, but yeah, maybe I don't go to there. Yeah, it is not going to have effect. Yeah. But anyway, yeah, you need a half spin.
Okay.
Yeah, for this purpose.
Okay.
Yeah. Or and you also need charge to have the magnetic moment. Okay. I think so. Okay. Anyway, so here the summary, right? All including the gamma you just mentioned, right? You can go back to take a look at all these equations. I should be able to share with you the book chapter this weekend soon. Okay. Okay. So we are done. We are done with this simple Larmor precession.